So let's see a little example. We're going to go through by hand and show what the derivative would be for a particular parameter. We have a model, and it says that so far at iteration t, w0 is equal to 0, w1 is equal to 1, and w2 equal to minus 2. This is our current estimate, wt. And the question is, how we're going to modify it, how we're going to compute the derivative, and we're going to compute the partial derivative of the likelihood function with respect to the parameter w1. And the parameter w1 is going to multiply the first feature, which is h1 of x, which in our case is number of awesomes. So what is the contribution that each one of these data points will have to the derivative with the equation above? That's what we're trying to do. So if you look at the equation above, for each one of these, we're going to make a prediction according to the current model as to whether that data point is actually a +1. So for the first one, which has 2 awesomes and 1 awful, we get the true label is +1, but our model only assigns 0.5 probability to it. So not perfect. What contribution does that have to the derivative? Well, let's just go through the equation above. So h1 of xi is the number on the left here, it's 2. And it multiplies the difference between the indicator function. Is this a positive example? Yes, it is a positive example. And the probability that we get from data, which is 0.5. So the contribution here is 2 times 1 minus 0.5, which is exactly equal to 1. Let's look at the next data point. The next data point, the h1 of x has value 0. So in this case, w1 is not important to it, but no, just let's go through. This is multiplying the indicator. Is this a positive example? In this case, it's not, so it's 0, minus the probability that the model assigns for this to be a positive label, which in this case is 0.02. And the total here, contribution, is going to be 0. It's interesting. For this particular data point, the model gets it extremely right. It says the probability is positive is very, 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 very small, 0.02, which means this is very likely to be a negative example, which in fact it is. It's 2 awfuls, 0 awesomes. Now let's look at the third example. It's a bit of an unusual example. It has 3 awesomes and 3 awfuls, and it is actually a negative example. And the model thinks it is pretty likely to be a negative example. So it's 0.05 probability of being positive, so 95% chances of being negative. So what's the contribution it has to the derivative? Okay, so let's look at h1 of x, in this case is 3. It multiplies the difference between the indicator that it is a positive example, so in this case is not, so it's 0, minus the probability assigned to the positive example, which is 0.05. If you multiply this together, you get minus 0.15. So that's the contribution. The contribution is negative to the gradient. Now for the final example, you have 4 awesomes, 1 awful. So 4 is h1 of x. It is a positive example, so the indicator has value 1. And the probability that the model thinks is positive is 0.88. So the contribution here is 4 that multiplies 1 minus 0.88, which is 0.12 times 4, 0.48. Great. And so the total derivative is just going to be the sum of each one of these contributions added up together. So the derivative of L computed at Wt with respect to the parameter W1 is just going to be the sum of these 4 contributions. So 1 plus 0 minus 0.15 plus 0.48, which is equal to, if you add it all together, 1.33. And now I'm going to do a little change of colors transformation here. Let's go to a color. Let's write the update rule for the parameter W1. We computed its derivative. Let's do the update. So W1 at the next iteration, iteration t plus 1, is going to be equal to W1 at iteration t plus eta the step size that multiplies the derivative of the likelihood function at Wt with respect to the parameter W1, which is the one that we're updating here. Now, let's suppose we set eta to be 0.1. It's a bit of a large number, but it makes our updates here a little simple. So what does this update rule says? W1 at iteration t plus 1 is W1 at iteration t, which was 1, plus eta 0.1 that multiplies the derivative we just computed right here, 1.33, which means that the new parameter is going to be equal to 1.133. We just made our parameter a little bit bigger, which is great.